look up at the night sky on any clear evening. Every point of light you see, every star twinkling in the darkness, shares something profound with our own sun. They are all at peace. But what does that really mean? What invisible forces keep these cosmic fires burning steadily for billions of years without consuming themselves in an instant? Tonight, you and I are going to explore the most common and yet most extraordinary phase in the life of a star. We call it the main sequence, and it is where the universe finds its equilibrium. Join me as we discover why stability is the cosmos's greatest achievement. Imagine if you could take a census of all the stars in the galaxy. If you counted every single luminous point in the Milky Way, you would discover something remarkable. About 9 out of every 10 stars you encounter would belong to the same family. They would all be main sequence stars. These are not the exotic supergiants you might see in telescope images, nor the strange, dense remnants of stellar death. These are simply stars that have found balance. They are the steady workers of the cosmos, the quiet majority, burning hydrogen in their cores and shining with a stability that can last for trillions of years. Why? Our own sun is one of them, and so are most of the stars you see with your eyes alone. But what exactly makes a star a main sequence star? The answer lies not in where it is in space, but in what it is doing. A main sequence star is one that is fusing hydrogen into helium in its core and doing so in a state of perfect balance. This is not a location or a moment in time. It is a phase of life, a state of being. Think of it as the adulthood of a star's existence. Just as humans spend most of their lives in a relatively stable phase between childhood and old age, stars spend the vast majority of their lifetimes on the main sequence. For some, this phase lasts mere millions of years. For others, it will continue for trillions. To understand what makes the main sequence so special, we need to step back and look at the bigger picture. In the early 20th century, two astronomers named Ejnar Hertzsprung and Henry Norris Russell independently made a discovery that would transform our understanding of stars. They plotted the luminosity of stars against their temperature, creating what we now call the Hertzsprung-Russell diagram. When they did this, something beautiful emerged. Most stars did not scatter randomly across the chart. Instead, they formed a distinct diagonal band running from the hot, bright upper left to the cool, dim lower right. This band is the main sequence. It is not just a pattern. It is the signature of stellar equilibrium. This diagram tells us something profound. It reveals that there is a relationship between how hot a star is and how brightly it shines. The hotter a main sequence star's surface, the more luminous it is. A cool red dwarf might glow with just a fraction of a percent of our sun's light, while a hot blue star can blaze with the brilliance of 100,000 suns. Yet all of these stars, despite their dramatic differences, share the same fundamental state. They are all fusing hydrogen in their cores. They are all in balance. The main sequence is not just a line on a diagram. It is the manifestation of physical laws that govern how stars burn and shine across the universe. You might wonder why this matters. Why should we care about a pattern on a chart created over a century ago? The answer is that the main sequence is the key to understanding stellar life itself. When astronomers observe a star and determine its position on the main sequence, they can infer an enormous amount of information. They can estimate its mass, its age, its temperature, and even predict how long it will continue to shine. The main sequence is like a cosmic ruler, allowing us to measure the properties of stars across vast distances. It connects the physics happening in a star's core with the light we observe from Earth. In this way, the main sequence becomes a bridge between theory and observation. So, where do you find main sequence stars? The answer is everywhere. They fill the spiral arms of galaxies, cluster in the hearts of globular clusters, and float in isolation through the depths of interstellar space. Some are members of binary systems, locked in gravitational dances with companions. Others, like our sun, journey alone through the cosmic dark. Some are young, having just settled onto the main sequence a few million years ago. Others are ancient, born when the universe itself was young. Yet regardless of their location or age, they all share that defining characteristic. They are stable. Woo! They are balanced. Peace. They are at peace. Our journey tonight will take us deep into the lives of these stars. We will witness the forces that hold them together and the fusion reactions that keep them shining. We will meet red dwarfs that will outlast galaxies and blue giants that burn themselves out in cosmic eye blinks. We will come to understand why our own sun sits exactly where it does on the main sequence and what that means for life on Earth. Most importantly, we will discover that the main sequence is not just about stars. It is about balance. It is about the fundamental principle that when opposing forces reach equilibrium, stability emerges. And in that stability, the universe finds its most enduring beauty. Every main sequence star begins its life the same way, not in balance, but in chaos. In the cold darkness between existing stars, clouds of hydrogen gas drift through space. These clouds are vast beyond comprehension, sometimes spanning hundreds of light years. For eons, they remain stable, their internal pressure balancing the gentle pull of their own gravity. But then something happens. Perhaps a nearby supernova sends a shockwave through the cloud. Perhaps two galaxies collide, compressing the gas between them. Whatever the trigger, a region of the cloud begins to collapse. Gravity starts to win. And from this collapse, a star will eventually be born. As the cloud collapses, the laws of physics ensure certain consequences. The material falls inward, and as it does, it heats up. This is not fire in any conventional sense. It is the conversion of gravitational potential energy into thermal energy. The faster the material falls, the hotter it becomes. At the center of the collapsing region, a protostar begins to form. This object is not yet a true star. It cannot fuse hydrogen, but it is shrinking, heating, and growing denser with every passing millennium. The protostar glows with infrared light, hidden from optical view by the cocoon of dust that surrounds it. But inside, conditions are changing. The protostar continues to contract for hundreds of thousands of years, perhaps even a few million years, depending on its mass. During this time, its core temperature climbs steadily. 1 million degrees. 5 million. 10 million. With each milestone, the conditions inside the core become more extreme. The hydrogen nuclei, stripped of their electrons by the intense heat, move faster and faster. They collide with increasing energy. And then, at last, when the core temperature reaches around 10 million degrees, something miraculous happens. The hydrogen nuclei collide with enough force to overcome the electrical repulsion between them. Nuclear fusion ignites in the core. The ignition of fusion is the defining moment in a star's life. It is the point at which a protostar becomes a true star. When hydrogen nuclei fuse to form helium, they release energy. This energy is what makes stars shine. But more importantly for our story tonight, this energy creates pressure. The intense heat and radiation generated by fusion push outward from the core. This outward pressure is exactly what the star needs. For the first time in its existence, the star has a force that can resist gravity's inward pull. The two forces reach an equilibrium. the star stops collapsing. It stabilizes. It has arrived on the main sequence. Think about what has just happened. A star spends the first chapter of its existence collapsing under its own gravity, growing hotter and denser. Then fusion ignites, and suddenly the collapse stops. The star finds balance. This is not a temporary pause. This is a stable equilibrium that can last for billions or even trillions of years. For the vast majority of a star's lifetime, it will remain on the main sequence, steadily fusing hydrogen into helium, steadily shining with the same luminosity. The chaotic process of birth has given way to the serenity of the main sequence. And across the universe, this process repeats itself endlessly. The journey from cloud to main sequence star is different for stars of different masses. A massive star, many times heavier than our Sun, will collapse quickly and reach the main sequence in just a few 100,000 years. Its intense gravity generates such high core temperatures that fusion ignites early and burns fiercely. A low-mass star, on the other hand, takes its time. With weaker gravity, the collapse is gentler and slower. It may take tens of millions of years for such a star to contract enough to ignite fusion. But once it does, it will remain on the main sequence far longer than its massive counterpart. The universe rewards patience. Regardless of mass, every star that reaches the main sequence shares a common milestone. They have all achieved what we call hydrostatic equilibrium. This is the state where the inward pull of gravity is perfectly balanced by the outward push of pressure from the hot fusing core. Hydrostatic equilibrium is the essence of the main sequence. It is why these stars are stable. It is why they shine steadily for so long. And it is the foundation upon which we will build our understanding as we continue our journey tonight. The star is born. The star is balanced. And now we can explore what that balance truly means. Hydrostatic equilibrium. The words might sound technical, but the concept is elegantly simple. Imagine you are holding an inflated balloon. The air inside pushes outward, while the rubber skin and atmospheric pressure push inward. The balloon maintains its shape because these forces balance. Now scale that up to a star. Gravity is always pulling every bit of the star's mass toward the center. If this were the only force, the star would collapse into a point. But fusion in the core generates tremendous heat and pressure, pushing outward. When these two forces are equal at every point within the star is in hydrostatic equilibrium. It neither collapses nor expands. It simply is. This equilibrium is not static in the sense of being frozen or unchanging. Energy is constantly flowing through the star. Photons of light created in the core work their way outward through the dense plasma, taking hundreds of thousands of years to reach the surface. Heat is transported by convection in the outer layers. The star is a dynamic, active object. Yet despite all this activity, the overall structure remains stable. The radius does not change significantly. The luminosity remains steady. The core temperature holds constant at the precise level needed to sustain fusion. Hydrostatic equilibrium is a dynamic balance, a continuous dance between opposing forces that somehow maintains perfect poise. What happens if this balance is disturbed? The star has a remarkable ability to correct itself. Suppose, for some reason, the fusion rate in the core increases slightly. More energy is released, the core heats up, and pressure increases. This extra pressure pushes the layers above outward, causing the star to expand slightly. As it expands, the core density decreases, which slows the fusion rate back down. The star returns to equilibrium. Conversely, if fusion slows, pressure drops, gravity compresses the core, density and temperature rise, and fusion speeds up again. The star is self-regulating. It has a kind of built-in thermostat that maintains stability. This self-regulating nature is one of the most beautiful aspects of main sequence stars. It means they are inherently stable over timescales that dwarf human comprehension. Our sun has been shining with roughly the same luminosity for over 4.5 billion years, and it will continue to do so for another 5 billion years. During all that time, hydrostatic equilibrium will maintain the sun's structure. Think about that for a moment. While continents have drifted across Earth's surface, while life has evolved from single cells to the complexity you see today, while countless species have risen and fallen, the sun has simply remained in balance. Steady, reliable, unchanging. The key to maintaining hydrostatic equilibrium is having enough fuel. A main sequence star is fusing hydrogen into helium, and as long as there is hydrogen in the core to fuse, the equilibrium can be maintained. The core of a star like our Sun contains an enormous reservoir of hydrogen. Even though it converts hundreds of millions of tons of hydrogen into helium every single second, the supply is so vast that it will last for billions of years. This is why the main sequence phase is so long. It is not that fusion is slow. It is that the fuel supply is immense. The star has time to shine steadily, to remain balanced, to nurture any worlds that might orbit it. Hydrostatic equilibrium also determines a star's structure. The pressure must be highest at the center, where it needs to support the weight of all the overlying layers. This means the core is the hottest and densest part of the star. As you move outward, the temperature and density gradually decrease. At the surface, the temperature might be a few thousand degrees, cool enough for atoms to hold on to some of their electrons. This temperature gradient, this layering from hot core to cool surface, is a direct consequence of maintaining balance. Every layer must have just enough pressure to support the weight above it and be supported by the pressure below. As you rest here tonight, consider this. The same principle that keeps a star from collapsing operates at every scale in the universe. Planets are held in spherical shapes by a balance between gravity and internal pressure. The atmospheres of worlds are maintained by a balance between gravity pulling down and thermal pressure pushing up. Even galaxies, in a way, are held together by a balance between the kinetic energy of stars and the gravitational pull of dark matter. Equilibrium is not unique to main sequence stars, but in these stars it reaches its most pure and enduring expression. Hydrostatic equilibrium is the reason the night sky is filled with steady, reliable lights. It is the foundation of stellar peace. Not all main sequence stars are created equal. If we journey to the cool end of the main sequence, we encounter the most common stars in the universe. Red dwarfs. These are small, dim stars with masses less than half that of our Sun. Some are as little as 8% of the Sun's mass, just barely massive enough to ignite fusion at all. Their surface temperatures are cool by stellar standards, often below 4,000 degrees. This gives them their characteristic deep red or orange color. To the naked eye, most red dwarfs are invisible. They are simply too faint. Yet they make up perhaps 3/4 of all main sequence stars in the galaxy. They are the universe's silent majority. Red dwarfs have low mass, and this has profound consequences. Because they have weak gravity, their cores are not as compressed as those of larger stars. The core temperature is lower, and fusion proceeds much more slowly. A red dwarf might generate less than 1% of the Sun's luminosity. Some of the smallest red dwarfs shine with just a 10,000th of the Sun's light. But here is the remarkable part. Because they burn their fuel so slowly, they can remain on the main sequence for an incredibly long time. A typical red dwarf will fuse hydrogen in its core for 1 trillion years or more. That is hundreds of times longer than the current age of the universe. Think about what this means. The universe is currently less than 14 billion years old. No red dwarf has yet exhausted its core hydrogen. Every single red dwarf that has ever formed is still on the main sequence. They have been shining since the early days of the cosmos, and they will continue to shine long after stars like our sun have perished. When the universe is 100 billion years old, the red dwarfs will still be there. When it is 1 trillion years old, they will persist. These modest, dim stars are the ultimate survivors. They are the cosmic misers, carefully rationing their fuel to achieve lifetimes that border on eternity. Red dwarfs also have another unique characteristic. Unlike larger stars, they are fully convective. Convection is the process by which hot material rises, cools, and then sinks back down. In a red dwarf, convection currents extend from the core all the way to the surface. This means that fresh hydrogen from the outer layers is constantly being mixed down into the core where it can be fused. In contrast, stars like our Sun only fuse the hydrogen in their cores. The outer layers remain separate. This convective mixing allows red dwarfs to use almost all of their hydrogen, not just the hydrogen in the core. They are extraordinarily efficient. Despite their longevity, red dwarfs are not always calm. Many are known to produce powerful stellar flares, sudden eruptions that can temporarily increase their brightness by a factor of 2 or more. These flares are driven by magnetic fields generated in the star's convective interior. When magnetic field lines become twisted and reconnect, they release enormous amounts of energy. For any planet orbiting close enough to a red dwarf to be in its habitable zone, such flares could be problematic. The radiation from a flare might strip away a planet's atmosphere or make the surface inhospitable to life. Yet despite this activity, red dwarfs remain fundamentally stable over the long term. The flares are outbursts, not signs of instability. Because red dwarfs are so common and so long-lived, astronomers have become very interested in planets that orbit them. Many red dwarfs are known to host rocky planets, and some of these planets orbit in the habitable zone where liquid water could exist on the surface. The closest known exoplanet to Earth, Proxima Centauri b, orbits a red dwarf. If life can adapt to the challenges of a red dwarf's environment, including the flares and the fact that planets must orbit very close to stay warm, then red dwarfs might be the most common hosts of life in the galaxy. They offer something no other star can provide: time. Trillions of years of stable, if dim, illumination. Red dwarfs remind us that bigger is not always better. These small, cool stars may lack the brilliance of blue giants or the familiarity of sun-like stars, but they have something else: endurance. They are proof that the universe values longevity over spectacle. In the vast sweep of cosmic time, it is not the brightest stars that will see the furthest future. It is the dimmest. The red dwarfs will be the last main sequence stars shining when the universe grows old and cold. They are the quiet lights that will guide the cosmos through its final, longest chapter. And tonight, as we explore the main sequence, we honor them. Misers, the survivors, whites. The eternal lights. Move toward the middle of the main sequence, and you encounter stars like our own sun. These are often called yellow dwarfs, though the term is somewhat misleading. The sun is not yellow in space, white. It is white, but its spectral type, G2, places it firmly in the middle range of main sequence stars. It is neither small and cool like a red dwarf, nor large and hot like a blue giant. It sits in what we might call the golden mean of stellar existence. Not too hot, not too cool, not too massive, not too small. Just right for stability, longevity, and perhaps for nurturing life on worlds that orbit it. The sun has a mass of about 2 × 10⁻³ kilograms. That might not mean much to you, so think of it this way. You could fit over 1 million Earths inside the Sun. Yet compared to the largest stars, the Sun is modest. Its surface temperature is around 5,700 degrees, hot enough to glow with a white light that our eyes perceive as slightly yellow filtered through Earth's atmosphere. The Sun's luminosity is defined as 1 solar luminosity, a standard unit by which we measure other stars. It is neither especially bright nor especially dim. It is, in the truest sense, average. And that averageness is part of what makes it special. Inside the Sun's core, conditions are extreme beyond imagination. The temperature is around 15 million degrees. The pressure is over 200 billion times that of Earth's atmosphere at sea level. Under these conditions, hydrogen nuclei move at incredible speeds. When they collide, they fuse via the proton-proton chain reaction. 4 hydrogen nuclei combine through a series of steps to create 1 helium nucleus. The helium nucleus has slightly less mass than the 4 protons that formed it. That missing mass is converted into energy according to Einstein's famous equation. The energy released by this fusion is what powers the Sun, and by extension, nearly all life on Earth. The energy released in the core does not immediately reach the surface. Photons produced by fusion are absorbed and re-emitted countless times as they work their way outward through the dense plasma. This process is called radiative diffusion, and it is incredibly slow. A single photon might take 100,000 years or more to travel from the core to the surface. Once it reaches the Sun's convection zone, hot plasma carries the energy the rest of the way, and the photon finally escapes into space. 8 minutes later, it arrives at Earth. The light warming your skin on a sunny day began its journey in the Sun's core over 100 millennia ago. It is ancient light, patient light. The Sun is currently about 4.5 billion years old. It has been on the main sequence for all of that time, steadily fusing hydrogen in its core. It is expected to remain on the main sequence for another 5 billion years or so before the core hydrogen is exhausted. This gives the Sun a total main sequence lifetime of about 10 billion years. For roughly half of that time, the Sun has already lived. It is middle-aged. During its time on the main sequence, the Sun has been remarkably stable. Its luminosity has increased by about 30% over the past 4 billion years, a gradual change that has allowed life on Earth to adapt. What makes stars like the Sun so special is that they are stable enough to allow complex chemistry and biology to develop on nearby planets. Red dwarfs may last longer, but their habitable zones are close, and flares can be dangerous. Massive blue stars burn out too quickly for complex life to evolve. But a star like the Sun offers billions of years of steady illumination at a comfortable distance. This stability has given life on Earth time to evolve from simple organisms to the incredible diversity we see today. The Sun's position on the main sequence, its temperature, its luminosity, and its longevity are all perfectly suited to nurturing a biosphere. When you look up at the Sun, you are seeing a star in its prime. It is not young and reckless, nor old and dying. It is balanced, mature, and reliable. It has been shining since before the dinosaurs walked the Earth, and it will continue to shine long after our current era ends. The Sun is a reminder that the middle path, the path of moderation and balance, can be the most enduring. It is not the most spectacular star in the sky, but it is ours. And in its golden, steady light, we find the energy that powers our world, the warmth that makes life possible, and the stability that allows us to thrive. The Sun is the quintessential main sequence star. Travel now to the other end of the main sequence. Here we find stars that are the opposites of red dwarfs in almost every way. Blue giants. These are massive stars, often 10 times the mass of the Sun or more. Their cores are so hot and compressed that fusion proceeds at a furious rate. Their surface temperatures can exceed 30,000 degrees, giving them a brilliant blue-white color. They are among the most luminous objects in the galaxy. A single blue giant can shine with the light of tens of thousands or even hundreds of thousands of suns. They are the cosmic beacons, the lighthouses of the universe, and they burn through their fuel at an astonishing speed. Why are blue giants so bright? The answer lies in their mass. A more massive star has stronger gravity, which compresses the core to higher temperatures and densities. At these extreme conditions, fusion happens much faster. The relationship between mass and luminosity is steep. A star that is 10 times more massive than the Sun is not 10 times brighter. It is thousands of times brighter. This is because nuclear reaction rates increase dramatically with temperature. A small increase in core temperature leads to a huge increase in fusion rate. Blue giants are stellar furnaces, burning at temperatures that make our Sun seem almost cool by comparison. The intense luminosity of blue giants comes at a cost. They exhaust their hydrogen fuel much more quickly than smaller stars. While a red dwarf might remain on the main sequence for 1 trillion years and the Sun for 10 billion years, a massive blue giant might spend only a few million years fusing hydrogen in its core. Some of the most massive stars spend less than 1 million years on the main sequence. They are born, live their entire main sequence life, and die in the cosmic blink of an eye. For these stars, the main sequence is not a long, leisurely phase. It is a brief, brilliant moment. They burn bright but brief. In the cores of the most massive blue giants, fusion proceeds via a different mechanism than in Sun-like stars. Instead of the proton-proton chain, they use the CNO cycle. CNO stands for carbon, nitrogen, and oxygen. These elements act as catalysts, facilitating the fusion of hydrogen into helium. The CNO cycle is much more sensitive to temperature than the proton-proton chain. Even a small increase in temperature greatly increases the CNO cycle's efficiency. This is why massive stars burn so hot and bright. Their cores reach temperatures where the CNO cycle dominates and fusion proceeds at breakneck speed. It is a positive feedback loop. More mass leads to higher temperature, which leads to faster fusion, which leads to immense luminosity. Blue giants are so massive and luminous that they can significantly affect their surroundings. Their intense radiation heats nearby gas and dust, ionizing hydrogen and causing it to glow. This creates emission nebulae, regions of space lit up by the energy of hot young stars. Many of the most beautiful nebulae photographed by telescopes are powered by blue giants. The Orion Nebula, the Eagle Nebula, the Tarantula Nebula, all of these contain massive blue stars that flood their environments with ultraviolet light. These stars are not just bright, they are sculptors, shaping the interstellar medium with their powerful stellar winds and radiation. They leave their mark on the cosmos. Despite their power, blue giants are still main sequence stars. They are still in hydrostatic equilibrium. The same balance between gravity and pressure that stabilizes a red dwarf also stabilizes a blue giant. The only difference is the scale. The core of a blue giant must generate enough pressure to support a vastly greater mass. This requires higher temperatures and faster fusion. But the principle is the same. As long as fusion continues, the star remains stable. When the core hydrogen is exhausted, the balance will break and the star will leave the main sequence. But for now, the blue giant shines in equilibrium, a testament to the universality of the laws governing stellar structure. Blue giants are rare. Because they burn through their fuel so quickly, there are relatively few of them in existence at any given time. Yet they are easy to spot. Their immense luminosity means they can be seen from vast distances. Many of the brightest stars in our night sky are blue giants or their close cousins. E, Rigel in Orion. Spica in Virgo, Regulus in Leo. These are massive stars that draw the eye, stars that have inspired myths and guided navigators. They are the showstoppers of the main sequence, proving that even in a state of balance, stars can achieve staggering brightness. They are proof that intensity and equilibrium can coexist. They burn bright, they burn fast, and they leave an indelible impression. We have spoken often of fusion, but what is it really? At its most basic, nuclear fusion is the process by which lighter atomic nuclei combine to form heavier nuclei, releasing energy in the process. This is the opposite of fission, where heavy nuclei split apart. Fusion is the power source of the stars. It is what allows a cloud of hydrogen gas to become a shining beacon that can illuminate planets for billions of years. Without fusion, there would be no main sequence. Without fusion, the universe would be dark and cold. Fusion is the alchemy that transforms mere matter into light and energy, and it happens continuously in the cores of stars all across the cosmos. For fusion to occur, two nuclei must be brought extremely close together. This is not easy. All atomic nuclei are positively charged, and like charges repel. The electromagnetic force pushes nuclei apart with tremendous strength. To overcome this repulsion, nuclei must collide with enormous energy. This requires incredible temperatures. At a few million degrees, nuclei have enough kinetic energy to overcome the repulsion and approach close enough for the strong nuclear force to take over. The strong force is attractive, but it only operates over very short distances. Once nuclei are close enough, the strong force binds them together and fusion occurs. Temperature is the key that unlocks the fusion reaction. In stars like the Sun, fusion proceeds via the proton-proton chain. This is a multi-step process. First, two protons collide and fuse to form a deuterium nucleus, a heavy isotope of hydrogen. One of the protons converts into a neutron, releasing a positron and a neutrino. Next, the deuterium nucleus fuses with another proton to create helium-3, releasing a gamma-ray photon. Finally, two helium-3 nuclei collide to form helium-4, releasing two protons in the process. The net result is that 4 protons have been converted into one helium. 4 nucleus, 2 positrons, 2 neutrinos, and several photons. It is a complex dance of particles, all happening in the star's core. The helium-4 nucleus created by fusion has a mass that is slightly less than the combined mass of the 4 protons that formed it. About 0.7% of the original mass has disappeared. Where did it go? Where did it go? It was converted into energy. This is the meaning of Einstein's equation, E equals mc squared. A small amount of mass, when converted to energy, yields an enormous amount of energy because the speed of light squared is such a large number. This is why fusion is so powerful. The missing mass from every fusion reaction becomes the energy that heats the star's core and ultimately emerges as light. Every photon the sun emits comes from the mass of hydrogen that was transformed in its core. The energy released by fusion does not remain in the core. It must escape, and this process takes time. Photons are absorbed and re-emitted countless times as they work their way through the star's dense interior. Each absorption and re-emission randomizes the photon's direction, so the path from core to surface is a drunkard's walk, zigzagging endlessly. This is why it takes so long for energy to reach the surface. But eventually, after thousands or hundreds of thousands of years, the energy does escape. When it does, it carries information about the star's interior with it. By studying the light from a star, astronomers can infer the conditions in its core, even though that core is hidden beneath layers of opaque plasma. Fusion also produces neutrinos. These are ghostly particles with almost no mass and no electric charge. They interact so weakly with matter that they can pass through the entire star without being absorbed. Neutrinos produced in the sun's core escape within seconds, streaming out into space at nearly the speed of light. Some of them pass through Earth, through you, without any interaction. Detecting these neutrinos is extraordinarily difficult, but astronomers have succeeded. By capturing solar neutrinos, scientists can peer directly into the sun's core, seeing the fusion reactions as they happen. Neutrinos are messengers from the heart of the star, bringing news from a place we can never visit. Fusion is not just the power source of stars. It is also the creator of elements. When the universe began, it contained only hydrogen, helium, and trace amounts of lithium. Every other element, from the carbon in your body to the oxygen you breathe, was created by fusion in stars. Main sequence stars create helium from hydrogen. Later, when stars leave the main sequence and become giants, they fuse helium into carbon and oxygen. The most massive stars go further, creating neon, magnesium, silicon, and ultimately iron. When these stars die in supernova explosions, they scatter these elements into space, enriching the interstellar medium. We are made of star stuff. The atoms in your body were forged in the cores of ancient stars. Fusion connects us to the cosmos. The light that escapes from a star carries with it a wealth of information. When we pass starlight through a prism or a diffraction grating, it spreads out into a spectrum, a rainbow of colors from red to violet. But this is not a smooth, continuous rainbow. The spectrum is crossed by dark lines called absorption lines. These lines are the fingerprints of elements in the star's outer layers. As photons from the hot interior pass through the cooler outer atmosphere, atoms absorb light at specific wavelengths corresponding to their energy levels. By studying these absorption lines, astronomers can determine what elements are present in the star, how hot it is, how fast it is moving, and even whether it has a magnetic field. Main sequence stars are classified by their spectra into types labeled O, B, A, F, G, K, and M. This sequence runs from hottest to coolest. O-type stars are the hottest and most massive, with surface temperatures above 30,000 degrees. They are blue-white and extremely luminous. Type stars are the coolest, with surface temperatures below 4,000 degrees. Guesses, they are red and dim. Our Sun is a G-type star, placing it in the middle of this sequence. Each spectral type has characteristic absorption lines. O stars have lines from highly ionized helium. Stars have lines from molecules like titanium oxide. The spectrum reveals the star's temperature and composition at a glance. Why do hotter stars appear blue while cooler stars appear red? The answer lies in Wien's law, which states that hotter objects emit most of their light at shorter wavelengths. Blue light has a shorter wavelength than red light. A hot star's peak emission is in the blue or ultraviolet part of the spectrum, so it appears blue to our eyes. A cool star's peak emission is in the red or infrared, so it appears red. The Sun, with its intermediate temperature, emits most of its light in the green part of the spectrum. But because the Sun emits light at all visible wavelengths relatively evenly, it appears white. The color of a star is a direct indicator of its surface temperature. The spectrum also tells us about a star's motion. If a star is moving toward us, the wavelengths of its light are compressed, shifting toward the blue end of the spectrum. This is called blue shift. If a star is moving away, the wavelengths are stretched, shifting toward the red. This is redshift. By measuring these shifts, astronomers can determine a star's radial velocity, how fast it is moving toward or away from us. This technique has been used to discover thousands of exoplanets. When a planet orbits a star, it causes the star to wobble slightly. This wobble produces tiny shifts in the star's spectrum, revealing the planet's presence. The spectrum is a tool of discovery. The absorption lines in a star's spectrum are not always simple and clean. Sometimes they are broadened by rotation. When a star spins, one side moves toward us and the other moves away. This causes some of the light to be blue shifted and some to be red shifted, broadening the absorption lines. By measuring this broadening, astronomers can determine how fast the star is rotating. Some main sequence stars spin very rapidly, completing a rotation in just a few hours. Others, like the Sun, rotate slowly, taking weeks to complete a single turn. Rotation affects a star's magnetic field and its surface activity, so understanding rotation is important for understanding stellar behavior. Some stars have spectra that show emission lines instead of absorption lines. These are lines that are brighter than the surrounding continuum. Emission lines are produced when atoms in a hot, low-density gas are excited and then emit light at specific wavelengths. Young, active stars often show emission lines from hydrogen, indicating the presence of hot, ionized gas in their outer atmospheres or in circumstellar disks. Even on the main sequence, stars can be dynamic and active. Their spectra reveal flares, prominences, and other signs of magnetic activity. The spectrum is not just a static snapshot. It captures the star's behavior and personality. When you look at a star with your eyes, you see a single point of light. But when you spread that light into a spectrum, you unlock a universe of information. You can learn the star's temperature, its composition, its velocity, its rotation, and its magnetic field. You can discover planets orbiting the star. You can trace the star's age and predict its future. The spectrum is the astronomer's most powerful tool. It transforms a distant point of light into a laboratory where the laws of physics reveal themselves. Every star tells a story, and the spectrum is how we read it. As we continue our journey tonight, remember that the beauty of starlight is more than visual. It is information waiting to be decoded. How long does a star remain on the main sequence? We have touched on this question, but now let us explore it in depth. The main sequence lifetime of a star is determined primarily by its mass. More massive stars have more fuel, but they burn through it much faster. Less massive stars have less fuel, but they burn it far more slowly. The relationship is not linear. It is exponential. A star 10 times more massive than the Sun does not live 10 times shorter on the main sequence. It lives hundreds of times shorter. This is because luminosity increases dramatically with mass, and lifetime is inversely proportional to luminosity. For the smallest red dwarfs, those with just 8 to 10% of the Sun's mass, the main sequence lifetime is astonishing. Calculations suggest these stars could remain on the main sequence for several trillion years. That is far longer than the current age of the universe. In fact, no red dwarf has yet left the main sequence. Every red dwarf ever born is still in the prime of its life. When you look at a red dwarf, you are looking at a star that will outlive galaxies. It will shine on long after the Milky Way has collided with Andromeda, long after most other stars have died. The red dwarfs will be the last lights in the universe. Stars similar to the Sun, with masses between about 80% and 120% of the Sun's mass, have main sequence lifetimes in the range of 8 to 12 billion years. The Sun itself will spend about 10 billion years on the main sequence. It is currently 4.5 billion years into that phase, making it middle-aged. For stars like the Sun, the main sequence lifetime is long enough for planets to form, cool, and develop complex life. This is why we exist. The Sun's stability over billions of years has allowed Earth's biosphere to evolve. A shorter-lived star would not offer enough time. A longer-lived star might be too cool and dim. The Sun's lifetime is well suited for life. For stars significantly more massive than the Sun, the main sequence lifetime drops sharply. A star with 5 times the Sun's mass might remain on the main sequence for only about 100 million years. A star with 10 times the Sun's mass will spend perhaps 20 million years as a main sequence star. And the most massive stars, those with tens of solar masses, burn through their hydrogen in just a few million years. These stars are born, live, and die in the time it takes the Sun to complete a tiny fraction of its journey around the galaxy. They are cosmic mayflies, brilliant but fleeting. Why do we care about main sequence lifetimes? Because they have profound implications for galactic evolution and the possibility of life. The stars that formed early in the universe's history, billions of years ago, have had time to leave the main sequence and die. Some became white dwarfs, others exploded as supernovae. These deaths enriched the interstellar medium with heavy elements, the raw materials for planets and life. Subsequent generations of stars, including our Sun, formed from this enriched material. The lifetimes of stars determine the pace at which the universe evolves chemically. Without short-lived massive stars to produce and distribute heavy elements, there could be no rocky planets, no water, no life as we know it. Astronomers can use main sequence lifetimes to estimate the ages of star clusters. When a cluster forms, stars of all masses are born at roughly the same time. The most massive stars leave the main sequence first, becoming giants. By identifying which stars are still on the main sequence and which have evolved off it, astronomers can determine when the cluster formed. This technique, called main sequence turn-off dating, has been used to measure the ages of globular clusters, some of the oldest objects in the galaxy. These clusters are over 12 billion years old, nearly as old as the universe itself. The main sequence is not just a phase of stellar life, it is a cosmic clock. As you rest here, consider the immense span of time represented by the main sequence. For the smallest stars, it is trillions of years. For the largest, just millions. Yet all of them, regardless of their lifetimes, are governed by the same physics. They all fuse hydrogen. They all maintain hydrostatic equilibrium. They all shine with the energy released by turning matter into light. The main sequence is a testament to the fact that physical laws are universal and timeless. Time may vary from star to star, but the principles remain constant. And in that constancy we find something profound. The universe is predictable, knowable, and filled with patterns that reveal the underlying order of creation. The main sequence is one such pattern, elegant and enduring. The main sequence is defined by stability, but it is not entirely unchanging. Even as a star remains in hydrostatic equilibrium, slow changes occur over billions of years. As hydrogen in the core is converted into helium, the mean molecular weight of the core increases. Helium nuclei are heavier than hydrogen nuclei, so the core becomes denser. To maintain pressure and support the overlying layers, the core must contract slightly and heat up. This increases the fusion rate, which increases the star's luminosity. Over the course of its main sequence, life, a star gradually becomes brighter. The Sun, for instance, was about 30% less luminous 4.5 billion years ago than it is today. This gradual increase in luminosity has important consequences for planets. When the Sun was young, Earth received less energy and should have been colder. Yet geological evidence suggests that liquid water existed on Earth's surface even then. This puzzle is known as the faint young sun paradox. The likely explanation involves Earth's early atmosphere, which may have contained more greenhouse gases, trapping heat and keeping the planet warm despite the dimmer sun. As the Sun has brightened over time, Earth's atmosphere has evolved, maintaining a relatively stable climate. It is a delicate balance, one that has allowed life to persist through billions of years of gradual stellar change. As a star ages on the main sequence, the helium core grows. Helium ash accumulates at the center, inert and unable to fuse at main sequence temperatures. The core becomes layered with a helium center surrounded by a hydrogen-fusing shell. Eventually, when enough helium has accumulated and the core hydrogen is exhausted, the main sequence phase ends. The core contracts, the outer layers expand, and the star begins its ascent up the red giant branch. But until that moment, the star remains on the main sequence, fusing hydrogen in its core and maintaining equilibrium. The transition is gradual, not sudden. There is no single instant when a star leaves the main sequence. It is a continuous evolution. Main sequence stars can also exhibit variability. Some stars pulsate, expanding and contracting rhythmically as sound waves reverberate through their interiors. These are called variable stars, and they are useful to astronomers because their pulsation periods are related to their luminosities. By measuring how fast a star pulsates, we can determine how bright it truly is, which allows us to calculate its distance. Other main sequence stars flare unpredictably, especially red dwarfs. These flares are driven by magnetic reconnection events, similar to solar flares, but often much more powerful relative to the star's total output. Even on the main sequence, stars are not perfectly calm. They are dynamic, living objects. The rotation of a star can also change over time. Young main sequence stars often rotate rapidly, but as they age, they can lose angular momentum through stellar winds, streams of charged particles that carry the star's magnetic field into space. The interaction between the magnetic field and the wind acts like a brake, slowing the star's rotation. This process is called magnetic braking. The sun rotates once every 25 days at its equator. When it was young, it likely rotated much faster, perhaps once every few days. Over billions of years, the sun has spun down. This evolution affects the star's magnetic activity and the conditions in its habitable zone. Despite these changes, the main sequence phase is still characterized by stability. The changes are slow and predictable. They do not disrupt the star's equilibrium. A star on the main sequence is in the most stable phase of its life. It is not the violent chaos of the protostellar phase, nor the dramatic expansion and contraction of the giant phase. It is steady, reliable, and peaceful. For billions of years, a main sequence star shines with the same approximate luminosity, temperature, and color. This stability is what makes the main sequence so special. It is a haven of constancy in a universe that is constantly changing. When we think about stability and change, we realize they are not opposites. They coexist. A main sequence star is stable overall, yet it evolves. It maintains equilibrium, yet it ages. This duality is true throughout nature. Mountains appear unchanging, yet they erode over millennia. The climate appears stable, yet it shifts over centuries. And we, as individuals, maintain a sense of identity even as every cell in our bodies is eventually replaced. Stability is not the absence of change. It is change that is slow, gradual, and manageable. The main sequence teaches us that balance can accommodate evolution. And in that lesson, there is a kind of wisdom. We can change and grow while still remaining ourselves. Let us bring our focus back to the star we know best, Fly. It is a G2 type main sequence star, unremarkable by cosmic standards, yet utterly essential to us. The Sun formed about 4.5 billion years ago from a collapsing region of a molecular cloud. For the first 50 million years or so, it existed as a protostar, contracting and heating. Then fusion ignited, and the Sun settled onto the main sequence. It has been there ever since, steadily converting hydrogen into helium in its core, steadily shining with the light that makes life on Earth possible. For half of its main sequence lifetime, the Sun has nurtured our world. The sun's core is a furnace where temperatures reach 15 million degrees and pressures are unimaginable. Here, 400 million tons of hydrogen are converted into helium every single second. The mass difference is converted into energy according to Einstein's equation. This energy takes the form of gamma-ray photons and neutrinos. The neutrinos escape immediately, streaming out of the sun at nearly the speed of light. The photons, however, begin a long journey. They are absorbed and re-emitted countless times, gradually losing energy and shifting toward longer wavelengths. Eventually, after tens or hundreds of thousands of years, they emerge from the surface as visible light. The light warming you now is ancient. The sun's surface, the photosphere, is the layer we see. It is where photons finally escape into space. The temperature here is about 5,700 degrees, cool enough for atoms to exist, but still hot enough to glow brightly. The photosphere is not a solid surface. It is just the layer where the gas becomes transparent enough for light to escape. Above the photosphere lies the chromosphere, a thin layer visible during solar eclipses as a reddish ring. And beyond that is the corona, the sun's outer atmosphere, which is mysteriously much hotter than the surface. These layers are dynamic, shaped by magnetic fields and convection. The sun is constantly changing, even as it remains in equilibrium. The sun will remain on the main sequence for approximately another 5 billion years. During this time, it will continue to brighten slowly as helium accumulates in its core. Eventually, the core will run out of hydrogen. When this happens, fusion in the core will cease. The core will contract under gravity, heating up as it does so. The layers surrounding the core will heat up as well, and hydrogen fusion will ignite in a shell around the inert helium core. This shell burning will cause the sun to expand dramatically. The sun will leave the main sequence and become a red giant. Its outer layers will swell, possibly engulfing the inner planets, including Earth. The serene phase will end. As a red giant, the sun will fuse helium into carbon and oxygen in its core. This phase will last only a few 100 million years, a brief epilogue compared to the 10 billion years on the main sequence. Eventually, the sun will shed its outer layers in a series of gentle puffs, creating a planetary nebula. The core, now composed of carbon and oxygen, will remain as a white dwarf, a hot, dense ember slowly cooling over trillions of years. The sun's journey will be over, but that is still billions of years in the future. For now, the sun is middle-aged, stable, and shining steadily. It is in the prime of its life, and we are here to witness it. The sun's stability has been crucial for life on Earth. Liquid water has existed on Earth's surface for over 4 billion years, allowing life to emerge and evolve. The sun's steady output of energy has provided a consistent power source for photosynthesis, the process by which plants and other organisms convert sunlight into chemical energy. This energy flows through ecosystems, from plants to herbivores to carnivores. Ultimately, nearly all life on Earth is powered by the sun. We are, in a very real sense, children of a main sequence star. Our existence depends on the sun's ability to remain in balance, to fuse hydrogen steadily, to shine without dramatic variation. The main sequence makes life possible. When you step outside on a sunny day and feel the warmth on your skin, you are experiencing the energy of fusion. The photons hitting your skin began as gamma rays in the sun's core, created when hydrogen nuclei fused into helium. They traveled for hundreds of thousands of years through the sun's interior, emerging as visible light, crossing 93 million miles of space in 8 minutes, and finally reaching you. This is the connection we have with our star. The sun is not just an object in the sky. It is the source of our warmth, our light, and our life. It is a main sequence star, and its stability is our blessing. As we near the end of our journey tonight, Remember the sun. It is the reason we are here. We have traveled far tonight. We began by asking what makes a star a main sequence star. We learned that it is not a place or a moment, but a state of being. It is the phase of life when a star fuses hydrogen into helium in its core and exists in hydrostatic equilibrium. We discovered that the main sequence encompasses a vast diversity of stars, from tiny red dwarfs that will outlive the universe as we know it, to brilliant blue giants that burn out in cosmic eye blinks. Yet all of them share that fundamental balance: gravity pulling inward, pressure pushing outward, creation and destruction in perfect equilibrium. The main sequence is the essence of stellar stability. We explored the physics that makes the main sequence possible. We saw how fusion ignites when a protostar's core reaches 10 million degrees, how the energy released creates the pressure needed to resist gravity, and how this equilibrium can be maintained for billions or even trillions of years. We learned about the proton-proton chain and the CNO cycle, the mechanisms by which stars convert mass into energy. We witnessed the birth of light from the annihilation of matter, and we came to understand that fusion is not just the power source of stars. It is the creator of elements, the forge in which the raw materials for planets and life are made. We are stardust, and the main sequence is where our atoms were born. We examined the incredible diversity of main sequence stars. Red dwarfs with their cool surfaces and miserly fuel consumption will shine for trillions of years. Sun-like stars offer billions of years of stable illumination, long enough for life to emerge and evolve on orbiting planets. Blue giants burn with a ferocity that lights up entire nebulae, but their brilliance is fleeting. Each type of star has its role in the cosmic ecosystem. Red dwarfs are the enduring lights of the far future. Sun-like stars nurture biospheres. Blue giants enrich the galaxy with heavy elements. Together, they form the population of the main sequence, the most common and most important class of stars in the universe. We learned how to read the light of stars. The spectrum, that rainbow crossed by dark lines, is the key to unlocking stellar secrets. It tells us a star's temperature, composition, velocity, and magnetic field. It reveals the presence of planets and allows us to measure distances across the galaxy. Spectroscopy is the language of astrophysics, and the main sequence stars speak it fluently. Every main sequence star, from the dimmest red dwarf to the brightest blue giant, has a spectrum that tells its story. By learning to interpret these spectra, astronomers have mapped the structure of the galaxy and traced the evolution of stars across billions of years. The main sequence is not just visible light. It is information. We contemplated the immense timescales of the main sequence. For the smallest stars, the main sequence phase lasts trillions of years, far longer than the current age of the universe. For the most massive stars, it is over in a few million years. Yet all of them, during their time on the main sequence, are governed by the same physical laws. They all maintain hydrostatic equilibrium. They all fuse hydrogen into helium. They all convert mass into energy. The main sequence is a demonstration that the universe is orderly and comprehensible. The same principles apply to every star, regardless of mass or age. This universality is what makes science possible. It is what allows us to understand stars we will never visit. We focused on our own star, the Sun. We saw it as it is now, a middle-aged G-type main sequence star, shining steadily and nurturing life on Earth. We traced its past, from its formation in a molecular cloud to its arrival on the main sequence. We glimpsed its future, when it will leave the main sequence and become a red giant, eventually shedding its outer layers and leaving behind a white dwarf. The Sun is our anchor in the universe. It is the reason we exist. and it is fundamentally a main sequence star. Its stability, its longevity, and its energy output are all consequences of the physics we have explored tonight. Understanding the main sequence helps us understand our place in the cosmos. As we conclude our journey, I want you to take a moment and think about what the main sequence represents. It is more than a phase of stellar evolution. It is a testament to the principle of balance. When opposing forces reach equilibrium, stability emerges. And in that stability, beauty and complexity can flourish. This is true not just for stars, but for ecosystems, for civilizations, and even for individual lives. We thrive when we find balance. The main sequence is the universe showing us that balance is not only possible, but enduring. It is the cosmos at peace. And as you drift toward sleep tonight, let the image of a main sequence star, steady and serene, anchor your thoughts. The universe is vast and ancient, but it is also orderly. It is knowable, and you are a part of it. We have reached the end of our exploration. The main sequence, the phase where stars spend the vast majority of their lives, is defined by a simple but profound principle: balance. The inward pull of gravity and the outward push of fusion pressure reach an equilibrium that can last for billions or even trillions of years. This balance is the foundation of stellar stability. It is why the night sky is filled with steady, reliable lights. It is why life has had time to evolve on Earth. The main sequence is not the most dramatic phase of stellar evolution, but it is the most important. It is where the universe finds its peace, where stars shine steadily and patiently, nurturing worlds and giving time for complexity to emerge. Tonight, as you rest, remember that you too are part of this cosmic balance. You are made of atoms forged in stars, and you orbit a main sequence star that has shone steadily for billions of years. Sleep well, knowing the universe is both vast and orderly. Until next time, this is Ether, guiding you through the cosmos. Good night.